Okay, welcome to this video. We're going to talk about factorizing matrices, characteristic polynomials, eigenvalues and eigenvectors, which I like to call eigenthingies, and least squares regression on polynomials of various sizes, including but not limited to lines. So let's get started. Okay, so what we ended up with is a matrix over here that had ones on the diagonal, and it had just the upper triangular components were not dealt with. So we did Gaussian elimination followed by back substitution. When we got to this point, this thing could be thought of as a matrix U, meaning upper. What we didn't talk about was all those calculations that we did could have been saved off in a different matrix called L, which is lower, because all the actions we did ended up being actions to create zeros down here. So if we had kept track of all that work, we would have had a lower triangular matrix and an upper triangular matrix, and then you can put them together in such a way so that M is equal to L times U, or U times L, depending on what you're trying to do. Okay, so what happens in a typical textbook, in our textbook, is that we end up with just LU, matrix decomposition, but if you try to use NumPy, it works a little differently. So what NumPy does is it optimizes even further than what your textbook does. It actually does what's called PLU decomposition. So PLU are three matrices that multiply together to give you M, but all that P does is it permutes. It's all zeros and ones. So if it's like a 4x4 matrix, it's all zeros except for 4 ones, not on the diagonal. I mean, it could be on the diagonal, but not usually. If it's on the diagonal, you don't need it, right? Permute, permute only. This is lower only. And then this is upper only. So why would you want to do this? So by storing the matrices P, L, and U, it tells you the steps that you need to take to solve mx equals b for any x. And so that then you end up with the same thing where you said, okay, wait, if we did that work, then M inverse mx equals M inverse b, and then x equals M inverse b. Okay? So in the same type of situation where you might want to find M inverse, you might want to find PLU, because that further breaks down the work, because it turns out that it's easier to calculate this. It's easier to do the work to find the x's. And again, the situation we're looking at is if we're going to keep recycling this matrix M, if we're not just solving this as a one-off, but we're going to keep swapping out different x values and keeping the same M. You don't necessarily have to keep the same B, but you got to keep the same M. If you're going to be solving this problem over and over with the same matrix, then this work is probably worth the effort. You save your steps for later. So let me give you an example. Okay, so I'm going to do my from math import star and my import NumPy as MP. Now, I'm going to import some other things for this unit, import SciPy, and this is really annoying. We just imported SciPy, but you have to separately import SciPy lin alg, or you won't be able to access. If you try to use SciPy lin alg, it'll see no such module. So I don't know why they make you import it as a separate thing, but they do. Okay. Now I'm going to just create a matrix, and again I'm just using a list of lists inside, but because I'm in the NumPy, so I need to actually use their special array structure so that it will recognize what I'm doing and behave appropriately. But that is what it is. It's a price worth paying for the benefit of doing this. Now let me just check it before I hit enter. So I want 1103 2, 1, minus 1, 1, 3, minus 1, minus 1, 2, and minus 1, 2, 3, minus 1. Okay, great. So if I just type sci pi ln alg, and it's still called LU, strangely enough. It's called LU, but it's PLU. Okay, then you get this stuff back out, and it's like, whoa, that's a lot of writing. I just can't parse all that. So it's easier to just do the following, just to say, okay, fine. This is P, L, U equals this stuff, and then you can just look at P, L, and U separately. It's just easier to see, and it will be better for manipulations. Anyway, notice that the permutation matrix is, as I promised, it's just got n ones and the rest zeros. The lower triangular matrix is a lower triangular matrix, and in this case they put the ones on the diagonal in the lower triangular matrix, and in the upper triangular matrix they do not have ones on the diagonal. So you could have insisted on the U having ones on the diagonal, but in which case the L wouldn't. You can't insist on both of them having ones on the diagonal, unless possibly the permutation matrix looked different. I don't know. But anyway, this works. All these pieces fit together, and let's see how we would actually solve for x. So I'm going to go back to the drawing board here and describe what we've just done. So we have P, L, U equals M, and we want mx equals b. Knowing m and b, we want to solve for x. Okay? So how would we do that? Well, first of all, I'm going to write it this way, just see if it's any easier. PLU x equals b is our goal, and we're calling this part m. Okay, and this is the part we want. So I'm going to erase this just so we can sort of follow this logic here. So you could then say, okay, if PLU is m and we want x, why don't we just think about it this way? PLU x equals b. You can put little hats on those. I don't always. It's just kind of time consuming, and I can't type it very easily except in LaTeX. But anyway, I could just say, what if I just said P something B? So B, I need to find Z. So Z is now still bundled up inside. I could say, well, I know LUX equals Z, but I don't know how to find that either. Well, I could say the following. UX could equal Y. I guess I'll put hats on all these guys. I need to find LUX equals Z, but then actually it means I need to find UX equals Y. So what order can I find these in? I know U and I know X. So if I do this thing first, if I start by saying find X first, then I know it, and sorry, I did this backwards. Pretty obvious I did it backwards. The first thing I can find is Z with this setup, because I know that PZ equals B, and so now I have Z. Now I put Z here, and I find Y. So first I find Z, second I find Y, and third I find X. And you may say, okay, that's a lot of work. Well, it is, but if you actually analyze out the number of steps it takes, again, you have to sink the cost for finding PLU, but once you find PLU, each remaining step is actually really, really fast. So if you know you're going to be recycling this M, it might be worth your effort to break it down. Okay, so now that you know like the game plan, let's do this. We have our M in Python, so let's make up a B and see if this works. So let's go back to Python. We have the PLU. Let's just make a B. Do we have a B yet? B is equal to MP array 4, 1, minus 3, 4. So now we have a B. So remember, we can just do this the old way. We can just say NP linalg solve MB. And this is, again, this is our, I think this is the same problem we've been doing all along. So it's -1, 2, 0, 1. Don't forget that third component there is really a 0 because of the E -16, so it just looks like a number. It's just disguising as a number. Okay, now what we want to do is find Z. So let's go back and just find Z. That was our first goal, and that means, how do we want to find Z? Because we're treating this whole block as Z, and we want to solve P and B for Z. So let's try to do that. Z equals, well, it would help if I could get my mouse in there. Oh, good grief. Okay, my mouse is in there. Z equals NP linalg solve PB. What is Z? Z is this lovely thing. All right, so we have Z. Z is -3, 4, 1, 4. Pretty easy. Now what's the next step? We want to look over here and say, okay, we want to find Y. So we want to solve LZ to find Y. So let's do that. Y is equal to NP linalg solve. And we're going to solve LZ. What is Y? Okay, that's a little more interesting. It's -3, 3, 0, 2. Or 2.6 rather. Let's call it 2.6. Okay. So finally, what is our last step? We want to actually find X. And X is just, this is our normal problem now. We're at the bottom of our stack, and then you can have solve U and Y to get X. X is equal U and Y gives you X. Okay, so then you get -1, 2, 0, and 1. So why would you want to do that anyhow? Really, it's just Gaussian elimination, but we are saving the steps by splitting up the work at the halfway point. It looks like 3 steps, but don't forget P is just a permutation. It's really not a big deal. So really there's 2 matrices you're multiplying together. It doesn't always help, but it helps in the certain situations that we would want to use it. So let's just look at the basic analysis. Okay, here's a little bit of mathy notation. So Gaussian elimination with back substitution is order n cubed. You can't get something for nothing. It takes you order n cubed just to create that PLU matrix, which is almost what it takes you to create M inverse. So it's basically a similar type of situation. So if you want to solve PLU x equals b after PLU is already split, it only takes you another order n squared. It's much, much faster. So again, it's a situation, it's not for one-offs, it's where you want to reuse that PLU. Again, you want to solve many different systems that have the same overall structure, and you're going to be recycling the M. That's where you want to use either M inverse or PLU or something, which means you're going to offload a whole bunch of the work in advance, and then you're going to recycle that work. Okay, so that's what that is all about. Hopefully that makes sense, and we're going to move on to the next topic. Okay, characteristic polynomials. We're going to use these to find eigenvalues and eigenvectors. And you've all taken linear algebra, so the intent is that all this is a review. If for any reason it's not a review for you, please let me know so that we can spend a little time working on it. All right, but this should brush out the cobwebs from people's heads if it's been a while since they've taken it. Okay, so let's talk about what this means. Let's start with this action. Start with a 3D point. You return another 3D point. It could be any dimension, but it's easier to visualize this way. So start with x, y, z. Okay, a new x is x plus 2z. A new y is, let's say, y minus z. a new z is minus x plus y plus z. So what you would write is f of x, y, z is equal to x plus 2z, y minus z, minus x plus y plus z. So we literally take a point in 3D and create a linear function to define a new point in 3D. So I want you to think of this as being a way of moving one point to another location. We represent this as a matrix. Okay, so we've got ourselves a 3 by 3 matrix. We would like to know, so what we want to know hello, computer. Oh, good grief. I just want to type, please. It's not letting me type. Okay, question. Are there any input-output pairs that lie on a line through the origin? In other words, is there any such thing that looks like this somehow? This is C as a constant. Or any C value. Okay. So in the first case, the capital F means I'm applying a function. In the second case, it means I'm multiplying C. Okay, it's a scalar multiple. Okay, I'm going to do this out with algebra rather than matrices, just to make sure you get a physical sense of what I'm doing. Because I know the first time as an undergrad when I saw this, it just looked like numbers flying across the page. And when I stopped and just did it with algebra, everything made sense. And then what happened with the matrices made sense too. So I'm just going to slow it down and do it out in longhand algebra, just in case anybody's in that same situation. Okay, so the question is, if we take C and distribute it through our point, it's Cx, Cy, Cz, and based on the function we gave, x plus 2z and y minus z and so on and so forth, is this ever true? Is there ever a time when these 2 points, the input and the output, lie on the same line through the origin? Like you could just stretch through the origin to get from one to the other. If that's true, let's figure that out. Okay, so I just have 3 equations and 3 unknowns. So far should be pretty straightforward. Okay, well, what do we do when we're trying to solve? We usually put all the zeros on one side, so I'm going to push the Cx, Cy, and Cz over, but the Cx is going to join up with the x, and the Cy is going to join up with the y, and the Cz is going to join up with the z, and that way I'm going to factor that, so I'm going to get a whole bunch of 1 minus c's showing up. If you've seen 1 minus lambdas showing up on diagonals, this is exactly what we just did. Okay, so we want to find C together with some x, y, and z that satisfies this. So you can't just find C. It has to be find C with an x, y, z triple. However, there's a little extra freedom. We have 4 equations and 3 unknowns. C is not free. You can't just pick C, but you can just pick x, y, or z in the following way. If we had an x, y, z that worked, our x, our y, our z would work. So we could just say, we could pick x equals 1, for example. So we do have that freedom. The only snag we might hit is if x is required to be 0, then our work would jam up. So we're going to go out on a limb here and guess that x isn't entirely 0. So if x isn't 0, then we can pick x to be whatever else we want. And so we're going to pick it to be 1 and just see what happens. Okay, and so here is what happens if I presume x equals 1. So we're going to have to go back later, or potentially have to go back later, and presume x equals 0 and see if anything happens. But at least right now, we're going to see if this logic holds. We now have 3 equations and 3 unknowns. We are looking for C, and we're looking for a YZ pair, knowing that x equals 1 if we get this to all work out. I want you to pause this for a second, and you tell me if you can find a y and a z and a c that work with x equals 1. So this is what I'm seeing in my mind's eye. So I didn't initially write it out this way, but in my mind's eye, I see that actually I think I could get away with all of this if I just let k equals 0, z equals 0, then all I have to worry about is y. I mean, that's not possibly the only solution, but if k equals 0, z equals 0, y has to equal to, what does y equal? Hold on. Okay, so k equals 0, z equals 0, y equals 1, but that really means c equals 1, right? So we don't really care about k. K was just there as like to hold a place in my mind's eye. So this could work, and then what does that actually mean? We said x equals 1, and then that actually means whatever x is, y is, and z is 0. Okay, so we ask a question, did we find a solution? Did we succeed maybe? We have, in this case, we are guessing c equals 1 implies the vector or the solution that we're looking for is 1, 1, 0, or 2, 2, 0, etc. should stay in this like TT0 pattern. Let's try. Okay, so let's go back to our original situation we had up here with our equations, and let's see what happens if we simply let z equal 0 and we let x and y be the same. Do we get something that carries that same pattern? So the z's are going to go away completely, and x and y are going to be the same. So if x and y are the same, then this is going to be like S for same, the same amount. And then x and y cancel out. So if you start out with x and y being the same and z equals 0, the resulting calculation still causes x and y to be the same and z to be 0. Now, in this case, how far do we stretch from the original x and y? Actually, we didn't go anywhere. So like if x and y are 1, then x and y stay as 1. Okay, so the eigenvalue, or the amount it stretches, is 1, meaning it doesn't stretch at all, okay? And the eigenvector is 1, 1, 0. You can rescale that to your heart's content. You can say that the eigenvector is 1 over root 2, 1 over root 2, 0. That's fine by me. I don't care. But the point is you're going off in the correct direction. And then the next question is, well, we know that there's 3 equations and 3 unknowns. Have we like overlooked any other possible eigen thingies, eigen pairs? So let's think about this for a while. Okay, what I'm going to do next is I'm going to go out on a limb, so to speak, and say since z was 0 before, our eigenvector was x is 1, y is 1, z equals 0. If we want any kind of z component, let's guess that maybe z is non-zero, and since we can pick it to be whatever we want, let's just assume it's 1. Since z equals 0 previously, let's try z equals 1 this time and see if we can discover anything new. Okay, so let's go ahead and do that. Okay, so this time we let z equals 1 and see what kind of equations we get. And we get this kind of mess. So now we have 3 equations and 3 unknowns. And I'm going to take some lazy algebra way out. The first equation I'm going to solve for x is minus 2 over 1 minus c. The second one I'm going to solve for y. Okay, and then the third one, gee, what should I do? I guess I'll solve this one for c. Why not? C is equal to minus x plus y plus 1. How does that do me any good? Well, it does, because this c equals, we want to actually know what c is. So what we're going to do is combine all these using that last equation. So c equals, and then minus x is 2 over 1 minus c, and then y is 1 over 1 minus c, and then plus 1. And maybe you think I'm crazy, maybe I am. So I want you to pause the video And you can follow my instructions or you can find your own way of solving for C. But I want you to solve for C and then come back and let me know. Okay, so by one mechanism or another, you should have found C is equal to 1 plus or minus square root of 3i. Okay, so that's what you should get for C. And so now we found all three of our C's, which are actually eigenvalues. There's 1, and then there's 1 plus and minus square root of 3i. So those should be your solutions. I'm not going to go through all the gory details, what to do with them now, but you're going to be able to do that in the computer. Okay, so here's a question. There's got to be an easier way, right? So aren't we just trying to find out when these guys over here, right here, whoa, why can't I have the color I want to write with? We're trying to find out when those guys are linearly independent, or you can think of it this way, either those two sets of guys are the same. But you want to know when these guys are linearly independent. So what you could do is you could just stack these guys back up into a matrix and see when the determinant is 0. Okay, now how do you find a determinant? Well, I'm going to choose this column to expand upon, and you can expand upon any column you want. And if this is not exactly new to you, I think you should pause the video and expand this and set the determinant equal to 0, find the C's, and meet me on the other side. So go ahead and do that. I will pause and do some work and come back. Okay, here's a partway point. Notice I wrote in red everything I got from the first column, and I'm alternating signs. You're not going to notice I alternated signs because that middle one is 0, but I wrote as -0 to sort of emphasize that. And then I get to this situation where I have 1 minus C times quantity C squared minus 2C plus 4. So we should get, as before, we got our C equals 1 eigenvalue. And so we're going to take this guy and we're going to go ahead and use the quadratic formula. You do that yourself. And I get C is equal to 1 plus or minus the square root of 3i. And I just remembered I did this thing incorrectly, so I'm very sorry. I wrote this incorrectly. The I should be outside. My bad. Please fix that if you put that in your notes. Sorry. Sorry. Okay, but this is much easier because we can repeat these same steps. If you notice what I did before, I was just kind of hacking around until I found some X's, Y's, and Z's, and I found the C's afterwards. It turns out that conceptually it makes more sense to find the eigenvector first, but in reality it's easier to find the eigenvalue and then reverse engineer what the eigenvector must have been that went with it. But the important thing is to know that they come in pairs and that you have to find them together as pairs. Okay? So this whole thing has a name, and this particular thing we just located, this guy here, is called a characteristic polynomial. Okay, so this guy is your characteristic polynomial. And what you can do, so by hand this is very, very tedious, but just to complete one exercise, find the not quite real eigenvectors. We already know the real one, so let's go ahead and one time go through the gory details, and after that we'll, you might have a homework on that, but most of the time you're going to be doing this using Python. Okay, but it's good for the soul to just do it once by hand. So I'm going to chuck in C is 1 plus square root of 3i, and I'm going to see if I can find the eigenvector. So you guys can do that. I'll pause the video every so often to show you the progress. See how much of it you can do on your own. Okay, if you want to know how to start, you just take that matrix that we had and then replace c with 1 plus square root of 3i and see if you can figure out what the resulting x, y, and z has to be. Again, you can set x, y, or z arbitrarily. You can set one of them if you like. Okay, here's the next peek at the next level. So you want to look for an x, y, and z that makes this true. Okay, so I get these equations that I want to solve. I have too much freedom, and so I'm going to just let z equals 0, just because, I'm sorry, z equals 1, just to see if that helps, with the warning that if z is meant to be 0, we may have to go back and rework this or figure out what happens if z equals 0, but let's go ahead and let z equals 1. Okay, so this means that if z equals 0, then the first two equations follow, and the third equation follows. We hope means if we were allowed to let z equals 1. If we end up with a contradiction at this point, then we know we weren't allowed to let z equals 1. What might we do next? Okay, so if everything we've done so far is valid, then we can easily solve for x and y, and then this third condition turns into a test. If that works, then the ends justified the means, and the question remains, aha, you might get jammed up here because you might have forgotten how to deal with complex numbers. So we're going to pull this aside as a separate question. With complex values, it's a pay me now or pay me later type of situation. You can't get away with anything with complex values, and so I've been sort of willy-nilly and leaving the i's floating all over the place and the denominator, and so now I got to deal with that. So I'm going to multiply everything by 3i, and so I'm going to get, square root of 3i, and then is square root of 3i times square root of 3i, which gives me 3i squared, which is minus 3, and I'm happy. So I can conclude that if c is equal to 1 plus square root of 3i, this gives rise to an eigenvector that looks like this. Let me see, what was x again? 2 over square root of 3i minus 1 over square root of 3i, and what was z? We had already said z was 1. Now, when you do this on the computer, you'll get a totally different answer, because I'm pretty sure that the computer puts the i's in the third component. But we can verify that it is actually the same. So let's go over to Python. Okay, I still have my Python running from before, so I have my SciPy and my SciPy and my NumPy and my math, but my m is wrong. So because I'm dealing with a different problem right now, and so I have to change my m to be the new m. Okay, and my new m is 102, 0, 1 minus 1, minus 1, 1, 1. Okay, so now I get to show you this magical formula, this magical command, which gives you the characteristic polynomial. Now, if I just created this polynomial, I may get a little confused with which way the coefficients go. So in this case, it starts with lambda cubed. We were using c, so we're going to start using lambda because that's the more traditional thing. So you have to know that the highest power is the first component that comes out of poly. So let's just copy this here and then take it back into our notes and see if we can match it up with what we did. Okay, so here's where we found this polynomial. Let's see if we agree, because we didn't actually do the whole thing out. So let's see what happens. If we do this multiplication out, you get c squared minus 2c plus 4, and then we get a minus c cubed plus 2c squared minus 4c. Add this all together, what do we get? Minus c cubed plus 3c squared minus 6c plus 4, and that's totally fine. We just totally flipped this. Like the characteristic polynomial can be multiplied by a constant, so this is the same as saying f of x equals x cubed minus 3x squared plus 6x minus 4. That's another way of saying, well, I prefer x's over c's, but most people use lambdas. So we would write it as lambda cubed minus 3 lambda squared plus 6 lambda minus 4. But I'm not really hung up on whether you use a c or a lambda or an x. I really don't care. It's just a letter. So as long as you understand what it means, that's what I really care about. Okay, so you need to know that when you invoke this polynomial feature of NumPy, you're going to get the characteristic polynomial out of a matrix, and it's going to go in decreasing order of the terms. It's going to start with the highest order, lambda cubed, lambda squared, whatever, and it's going to be the power is 1 less than the number of elements. So if you have 4 elements, that means one of them has to be reserved for your constant, so the highest power is going to be 3. Okay? All right. Moving right along, back in the Python world, we need to know something about the eigenvalues and eigenvectors. I mean, we could just solve this because there's tools to solve the polynomial. I just don't want to go there. I would rather just now show you how to use the linear algebra tools, and that looks like a mess to me. So I'm going to actually store this as P and Q because I would rather look at P first, which is our eigenvalues, and then look at Q, which is the matrix for our eigenvectors. And I'm sorry about the display here because even if I stretch my screen, it won't put the third component next to the second component. I'm very sorry about that. But okay, so for capital P, we have our 2 complex eigenvalues. You can see they're a complex conjugate pair. They're right there. They're actually the same ones we just found, but they just put it in the proper format. Oh, by the way, J equals I. I don't know if I told you that before. Anyway, I think you would have figured that out by now. And this 1 plus 0j just means totally real 1. So the weird part is trying to figure out what the eigenvectors look like. And so you actually have to look at the columns of Q. So for example, if I want to look at Q00, 0, then I want to look at Q10, 0. I might type it out like this just to make it a little easier on my eyes. So this here is the eigenvector that goes with the first eigenvalue. And likewise, I could pull the third one, which is index 2. If it's just easier for you to type this, I'm sorry, I meant to do 0, 2, indexing, 1, 2, and 2, 2. Okay, so this should be the eigenvector that goes with that lambda that was 1, which was just when we did it by hand, we got 1, 1, 0. Okay, but what you can see here is that everything is scaled, and if you wanted to verify that this was all the same thing we figured out, you can divide by Q02 just in Python, and that will reassure you that indeed that's the same as 1, 1, 0, which is what we got. So you can just make use of Python. It's sitting there, and you can justify things to yourself that way. So for example, let's see, what else could I do here? Don't forget the e to the minus 17 or e to the minus 18 or e to the minus 16, all these guys. That's just indicating that that should be treated as a 0. That's round off error for our purposes, so that's a 0, that's a 0, for example. So just don't let that bother you. That's just not even there, okay, for the kind of problems we're working on. And furthermore, that's just the machine accuracy. So there's just a little bit of noise coming out, and don't let that bother you, okay? That's probably enough of that discussion. I'm going to go to the next thing. I'm going to talk to you a little bit about just your computer. So you can get this great thing, finfo. So in NumPy, there's something called finfo, and if you want to know how accurate your floating point can go, right here it tells you the resolution should be within like e to the minus 15. So right there, the computer itself is telling you anytime the exponent is lower than e to the negative 15, just treat everything as a 0. So definitely e to the negative 16 is 0 because it's below the resolution threshold. Okay, so that's a quick way to find out and reassure yourself that you know what your system is running and what Python you're running. So that can just be just like a little sanity check for you. Okay. So I wanted to sort of bring out this point that the square root of -1 is I or j, and that's just sort of annoying because you can't just type it in. And so you can kind of hack this a little bit. This is a problem, right? If we say square root of -1, it's not happy with us. So how do we deal with this? So here's what I recommend. This is really cheesy. I don't know what the correct way to do this is. But if I say -1 to the power 0.5, it seems to give me an I back out. So again, that garbage in front of, your real component is actually 0, and your imaginary component is 1, and so now you can kind of use this. I don't really like this solution, but it kind of works, and if you need something better, then let me know, and I'll help you scour the internet for a better solution. I don't think there's anything in your homework that requires you to use I like directly. You're going to see it coming back out. But if you should want it, this is a good hack. Anyway, let's continue. Okay, so what we have here is some homework problems are going to give you either extra degrees of freedom or the opposite, things that are inconsistent or overdefined. And so beware of that. That is intentional. So what would Python do to these types of problems? In this case, the first 2 rows are inconsistent, right? And we could easily have made them redundant by, for example, could have put a 20 here instead of a 7, and then it wouldn't have been inconsistent, but it would have been redundant, and so you get a different kind of behavior. So let's go ahead and put that in Python and see what Python does to it. Okay, so you have M and B that you already have from the work we were just doing, so I just typed those in. Now I'm going to try to solve this np-lin-alg solve, and I'm going to see how it crashes. Okay, so this is the kind of thing you can expect out of NumPy when you did nothing wrong, but there is something weird about your matrix or your problem, so you didn't type it in wrong. It's not a syntax error. It's a different kind of error. It's telling you, I'm sorry, I can't do what you just asked me to do. Okay? So if you do this, you might say, hey, I'm just curious, what's the determinant on that matrix? And you're like, aha, the determinant on that matrix is M, so I probably have something that's either inconsistent or redundant. So that's a clue. So if you get that kind of output, you can start encountering this and trying to figure it out. What happens if B is simply redundant instead of being inconsistent? Then what kind of output would you get? You're still going to get kind of garbage out. So just because you get that garbage back doesn't necessarily, it says singular matrix. Okay, so singular matrix is a dead giveaway that your determinant was 0. So you could also just read the output, but it's just kind of intimidating. So if you find that a little bit intimidating, you can just poke yourself and verify that yes, the determinant is 0. And so I'm going to have to poke a little bit by hand to figure out what is actually going on here. Okay. One tool you can use is, I think it's the same, okay, PLU is equal to sci-pi-lin-alg LU M, so PLU. Now, we found out that SciPy or NumPy got partway through the LU process, and the permutation matrix is fine, the lower triangular matrix is fine, but then when they went to do the backward substitution, something went wrong. Okay, so the U, look, the last row of U is all zeros, so that means something washed out. So this just gives you a little more information about what's happening in your matrix, and you say, okay, so I have one row that's either redundant or inconsistent. So M has some redundancy, but it's only 1 degree of redundancy. So this just gives you a little bit more information. You can do the following. If you want to do essentially by hand calculations, but you want the computer to do it, there's another package called SimPy, and that's why it's for this unit. This is why I asked you to install SimPy, to just help give you some more information out of this. And I'm going to put in my matrix here. It looks a little different. We're in a whole different world. We're not in NumPy anymore. It should feel very different. It should feel like it's a very real, very abstract world. It's not an applied world. It's more of your pure world, okay? And so you're going to ask for some pure calculations, reduced row echelon form, RREF, and it's going to do that reduced row echelon form for you. What this does is it gives a reduced format followed by a list of pivot elements. Okay? I'm going to show you another example of this. So your SimPy matrix doesn't look at all like your NumPy matrix. Although they're based on lists of lists, so if you wanted to analyze them both ways, you could, you can recycle some of that typing if it's going to be a lot of typing, of course. You could just make a list of lists and then feed that into both structures. Okay, so what happens with this system, M3 reduced row echelon form, is going to tell you that there's a bit of redundancy there. That's exactly the same thing we just did above, but this time we brought B along for the ride. So gives us not really a different example, but it's just showing you a different instance of the same example. But at least it brings a bit more analysis into play. Notice that there's fractions, it's not decimals, so this is very pure. You should feel like you're in some kind of a Maple or Mathematica environment when you're working with SimPy. It's actually there to do your homework for you, but I didn't tell you that. But that kind of feel, okay? So for any z, x and y are possible, I'm just going to take this output and I'm going to dump it into the external so that we can look at it a little more closely. Okay, so what does this mean? Let's just turn this into the answer. What does this look like? Okay, so this means that this means that I still don't have the ability to write on my screen, is what it means. What is with this computer? I don't know. It just keeps changing its mind about whether I'm allowed to write on the screen or not. Okay, so this we got from here. And then we're going to go for the next one, y plus 5/7 z is equal to 22/7, everybody's favorite fraction. Okay, and then what this last bit means is for any z, x and y are possible. Okay, so this is a line. And you could say, for example, let's find two solutions on this line. So one solution would be 26/7, 22/7, 0 is a solution. Hey, I didn't say I was going to pick the hard way out. So this is another. Okay, how did I find the first one? I just decided to be super lazy and do what? I just said that x and y and z are all 0, and then I said, okay, I can only use that trick once. So I'm going to let z be 1, and I can only use that trick once too. But anyway, I have 2 points. They uniquely determine a line, and there you go. Okay, So what does a non-solvable system end up looking like? Okay, so what about M4 is SimPy matrix 1, 2, 3, 10, 2, 4, 6, 7, rather than it being redundant. And then when we do M4 and we try to do RREF on that, reduced row echelon form, then it just gives us a slightly different output. So this is telling us that whereas before we had a string of zeros, that meant yes, this is all, you can do this. This is telling you there's an inconsistency. It's essentially saying if you have 0 x's, 0 y's, and 0 z's, you still end up with 1, which is bogus. Okay, so you get this kind of bogus answer in the last row, then you know that this is an inconsistent matrix. Okay, so those tools should be plenty to help you through your homework, and let me know if you have any questions.